All right. Good afternoon. Welcome, everyone. My name is Jeff Scott Brown. I am one of the co-founders of the Grails framework and the Grails practice lead at OCI. And what we're going to talk about this afternoon is metaprogramming techniques with Groovy. We'll get into, very quickly, we'll get into a definition of what I mean by that, and then we'll spend most of our time drilling into details and getting an understanding of a lot of the really cool features that Groovy has to offer to support really powerful metaprogramming techniques. So, first, just a little bit about me. So I live in St. Louis, Missouri, which is where OCI happens to be based. This is the St. Louis Arch, the gateway to the west. It's 600 and something feet tall, and this is the Mississippi River in the foreground there. So the arch is on the Missouri side of the river, and this picture looks like it's taken from the Illinois side of the river. St. Louis is a great city. If you're ever going to be in the area, let me know, and I'll be happy to connect with you, and we can go listen to some music or have some great food. I love St. Louis. This is not my family. This is just a picture of them. And it disappeared awfully quickly there. So I want to talk just a little bit about OCI and how OCI relates to Groovy and Grails. So earlier this year, in the spring of this year, OCI became the new home of Grails. So the Grails development team and the technology moved to OCI, which is where we are now, and things are going fantastic. So since April, we've released about a dozen releases of Grails, 3.0.1, 3.0.2, all the way up through 3.0.9. We've released 2 or 3 releases in the 2.5x chain, and we've released a couple of milestones for the upcoming Grails 3.1, which we're hoping to ship by the end of the year. Things are going just fantastic at OCI. I couldn't be more optimistic about the future of the technology there. We're actively growing the team and actively evolving the technology. And as I said, I couldn't be more optimistic about where we're going to be able to go with the technology now. OCI has been around for a long time, more than 20 years, and OCI has been an open source company for all of that time, and so now Grails is part of that open source portfolio of products. We've got clients all over the world in lots of different industries. This is a tiny subset of the folks that we're working with at OCI, but you can see there are a lot of giant name companies there that OCI has been working with for a very long time. Maybe one of the last things I want to say about OCI is we're hiring. We're actively growing the Grails team. We're hiring folks to do Groovy and Grails project work. That includes a lot of different kinds of Grails development. We're doing a lot of plugin migrations from Grails 2 to Grails 3. We're developing a lot of new plugins. We're expanding Gorm's reach to reach out to even more data stores than it does now. We're developing new application profiles, a lot more to come. In the coming months, you'll hear about some of the new application profiles that we're excited about for Grails 3.1. And there's a lot of Grails core development work going on. So we're hiring Grails developers to do all of these kinds of work. And if you're interested in talking to me about that, please let me know. You can contact me at brownj@ociweb.com, or you can send us a note at grailsjobs@ociweb.com. Unfortunately, I'm not going to be here all week. I've got to leave tomorrow morning. I've got obligations back in St. Louis later in the week. But if you'd like to talk to me this afternoon, I'd be happy to speak with you, or contact me via email, and I'll be happy to communicate with you that way. So more at ociweb.com/Grails. All right, so let's get right into the metaprogramming talk. So I want to start by agreeing, or at least identifying what I mean by metaprogramming. So metaprogramming is a term that kind of means different things to different folks in different contexts. And I'm going to talk about 2 fundamentally different kinds of metaprogramming. I'm going to talk about runtime metaprogramming, and then later I'm going to talk about compile time metaprogramming. And those are very different techniques. They've got some things in common, but they also serve kind of different purposes. And after we've been through a discussion of each of them, it'll be easier to talk about how they relate to each other. But first, I'm going to talk about runtime metaprogramming. And runtime metaprogramming is, at least what I mean when I say runtime metaprogramming here today, is I'm talking about a program modifying itself while it's running. So while the program is running, the program is modifying itself. So the program could be adding new methods to classes while the program is running. Remember, this is not happening at compile time. This is happening at runtime. So the program can be adding new methods to classes while the program is running. The program can be replacing existing methods. The program can be intercepting calls to methods or intercepting property access. That's the kind of metaprogramming that we're going to start with. Groovy's runtime metaprogramming capabilities is what I'm going to press into. So think of it as a Groovy program modifying itself while it's running. That's what we're going to start with. It turns out that Groovy lends itself very well to that kind of metaprogramming. So when you make a method call from Groovy, Groovy's syntax, of course, is very similar to Java's syntax. So if you've got an object reference called obj and you want to invoke a method called doit on that object reference, you would have something like obj.doit, and then maybe you'd have some parentheses after that. When you compile that code in Java, what the compiler generates for you is instructions that tell the runtime to go find the doit method in whatever type of object obj points to. So obj is a reference, it points to some object on the heap, and you've invoked obj.doit. The runtime can figure out what kind of object that is, and Java's polymorphism allows for a certain kind of dynamic dispatch there, where the runtime will figure out what type of object obj points to, and it will look to see if there's a doit method in that type. And if there is, that method gets executed. And if there's not, then Java knows how to navigate up the inheritance hierarchy until it finds where the doit method is implemented. And wherever it finds that method, that's the method that will be invoked. In Groovy, that exact same line of code, that obj.doit, the compiler will generate fundamentally different instructions for that. The compiler does not generate instructions that says, go find out what kind of object obj points to and then execute the doit method in that class. Instead, the Groovy compiler generates instructions that's really a request to the Groovy runtime system, part of the system called the MOP, or Meta Object Protocol. The compiler generates instructions that are really a request to the MOP, and the request includes several pieces of information. So the object that obj points to is passed to the MOP. The name of the method that you're trying to invoke, doit, is passed to the MOP, and then if you're passing any arguments, those are passed to the MOP. So now the MOP has all this information. It's got an object, a method name, and maybe some arguments. And what you've done is you've made a request for the MOP to carry that out somehow. And one of the things that might happen when you make that request is Groovy might find a doit method in the class that obj is an instance of and will execute that. So that would be very similar to what happens in Java. But there's a bunch of other stuff that might happen instead of that. And a lot of that is what I want to press into. That system that I just very briefly described is known as the MOP, is Groovy's dynamic dispatch mechanism. And that dynamic dispatch mechanism is where a whole lot of the really cool and really powerful features of the language come from. And we're going to press into that and get an understanding of at least how at least some of that stuff works. So Groovy has a very dynamic method dispatch mechanism that allows you to do things like intercept calls to methods and intercept access to properties. You can create methods at runtime. There's a whole lot of really, really cool stuff you can do on the JVM if you're using Groovy. And it turns out that, remember that Groovy runs on the JVM. Groovy does not really have its own platform or its own runtime environment. It kind of does, but it's all on top of the JVM. Everything that Groovy can do, the JVM is capable of, because when you run your Groovy code, it's running on the JVM. It turns out that the JVM supports really, really dynamic behavior, much more dynamic behavior than the Java programming language provides easy access to. So keep that in mind as we're looking at these all of these features that are involved in Groovy's runtime metaprogramming system. Keep in mind that all of this stuff is capable on the JVM. Groovy's taking advantage of the JVM's capability to support these kind of behaviors. But as I said, they're behaviors that the Java programming language just doesn't provide an easy way to get to. And I should have mentioned this earlier. If you've got questions, please speak up. I can only see about the first 3 rows here. I see there are a whole bunch of people here, but I can just barely make out that there are people. So raising your hand won't do. You'll have to just speak up, and that's not a problem. So if you've got a question or comment as we're moving along, please speak up, and we'll be happy to deal with that. Very good. All right, so I want to start by looking at a class that's provided by Groovy. There's a class provided by Groovy called Expando, and the slide you see here demonstrates some of the abilities that the Expando class supports. So I can create an instance of the Expando class and just make up properties that don't exist and assign them values, like myexpando.favoritelanguage equals Groovy. There really is no property in the Expando class called favorite language, but that line of code will in fact execute. And I want to be clear that this is not how objects behave in general in Groovy. There's code in particular in the Expando class that makes that possible. In general, if you write a class called person and you create an instance of the person class and you try to assign a value to a property that does not exist, that will result in a runtime error. You'll get a missing property exception. So it's not the case that in Groovy you can just make up objects or make up properties and assign them values. It's the case that the Expando class in particular has some code in it that allows you to do that, and we're going to understand how a lot of that works as we press along here. So myexpando.favoritelanguage equals Groovy is just making up a property that doesn't exist, favorite language, and assigning it a value, and that value is the string Groovy in this case. The next line of code says myexpando.addNumbers equals closure, right? That thing on the right-hand side of the equals is a closure. Groovy has supported closures pretty much all along since the beginning of Groovy. A closure is, think of it as a block of code. It has a lot of things in common with a method, but it's a first-class object that can be passed around the JVM. So myexpando.addNumbers equals closure, at least at one level, is really the same thing as the previous line, and that is I'm making up a property that doesn't exist, and I'm assigning it a value. The value that I'm assigning to favorite language is a string, happens to be the string Groovy, and the value that I'm assigning to add numbers is a closure. But I could assign any object to one of these made-up properties. So far we see a string and a closure being assigned to these properties. And then the next 2 lines, the first 2 assertions, are asserting that if I retrieve the value of, the first assertion anyway, is asserting that if I retrieve the value of one of these made-up properties, like favorite language, that will evaluate to the value that I assign to that property. So myexpando.favoritelanguage should evaluate to the string Groovy, and this code doesn't. These assertions do in fact pass. The second assertion is invoking a method that does not exist on the Expando class called addNumbers and passing in a couple of integers and expecting that the addNumbers method will return 100, and that is in fact what happens. So we'll figure out how that works in a moment. And then finally, the last assertion is describing what happens if I retrieve the value of a property on an instance of the Expando class and that property does not exist. And so what's being asserted here is that evaluates to null. I won't get a missing property exception or any kind of runtime exception. It'll just evaluate to null. Again, all of that is behavior that the Expando class in particular supports. In general, if you refer to a property that doesn't exist, you'll get a missing property exception from Groovy. And that's all by design. Does all that make sense? Good? All right, so let's start to drill into the dispatch mechanism and get a sense for how some of that works. So when you assign a value to a property in Groovy, like expando.favoritelanguage equals Groovy, remember what you're really doing there is sending a request to the mop. You're sending a request to Groovy and saying, here's an object, here's a property name, and here's a value. See if you can make that happen. One of the things that might happen as part of that request is Groovy will look at the object that Expando is an instance of and see if there's a method in that class called setProperty that accepts 2 arguments. And if there is, that method will be called. And in fact, that's how the expando class is intercepting that call to expando.favoriteLanguage equals groovy. The expando class has a method in it called setProperty that accepts 2 parameters. So now I can make up any property at all and assign it any value. And what Groovy is going to do with that is invoke the setProperty method on the expando instance and pass the property name as the first argument and the value as the second argument. And then it's up to the expando class to do whatever it needs to do inside of the setProperty method to keep track of mapping that property name to a value. We'll see what that looks like in just a minute. When I retrieve the value of a property, remember that, again, it's just a request to the mop that says, here's an object and here's a property name. See if you can evaluate that property, see if you can evaluate that expression. And one of the things that the mop will do is it will look at the object that expando is an instance of and check to see if there is a getProperty method in that class. And if there is, that getProperty method will be invoked and the property name will be passed as the sole argument to getProperty, and then getProperty can return whatever's appropriate. So in the expando class has this setProperty method and this getProperty method, and what the setProperty method is doing is simply putting entries in a map where favoriteLanguage is a key and groovy is the value. And then in getProperty, the expando class is simply looking in the map to retrieve the value that's associated with the key favoriteLanguage. So we'll write some real code in an IDE in a moment to exercise some of that, but that's really all that's going on there. And then finally, the last example here, we're invoking a method called addNumbers, and that method does not exist in the expando class. There's a whole series of things that Groovy will sort of step through anytime you make a method call from Groovy. So when I try to invoke the addNumbers method on the expando class, there's a whole series of places where that method might be handled. And at the very end of the line, once Groovy has checked every place where that method might have been handled, and all of them failed, generally Groovy will throw a missing method exception. So you've invoked a method that doesn't exist, you get a missing method exception. But one of the last things Groovy will do before throwing that missing method exception is Groovy will check to see if there's a method missing method in the class that expando is an instance of. So in this case, it'll be the expando class. And there is a method missing method in the expando class. So Groovy will invoke that instead of throwing a missing method exception. So let's jump into an IDE and exercise some of that. So we're gonna write a Spock specification here to experiment with some of those ideas. So I'm going to create an instance of a class that I've called Devoxx Expando, and right now Devoxx Expando is empty. There's nothing in that class. And I will make up a, we'll say company name equals OCI, and ex.favoriteLanguage equals groovy. And then I'll test that when I retrieve the value of company name, that it's equal to OCI, and when I retrieve the value of favoriteLanguage, that it is groovy. All right, that looks good. So let's run this test, and I expect this test to fail right now because the Devoxx Expando class is empty, and it failed right here at line 10. So if we look here at this exception, we see that dynamic expandable spec groovy line 10 is where the error happened. That's this guy right here. So I've tried to assign a value to a property that doesn't exist. And as I said before, in general, you can't do that in Groovy. But remember what Groovy is going to try to, one of the things that Groovy will try to do with this line of code is it will check to see if there's a setProperty method in the Devoxx Expando class. And if there is, setProperty will be invoked. Company name will be the first argument, and OCI will be the second argument. So let's make that happen. All right, something like that. And I'll leave the method empty for now. So let's run this. It's still going to fail, but it's going to fail in a different place. So here we see that the exception is happening on line 14 now. So lines 10 and 11 were successful. They didn't do anything, but they also didn't cause an exception to be thrown. What's happening when lines 10 and 11 get executed is Groovy is calling this set property method, which doesn't do anything right now, but Groovy doesn't know or care about that. All Groovy is doing is invoking the method, and you get to do whatever you want to do inside the method. The error is happening here at line 14 when I'm trying to retrieve the value of a property that doesn't exist. So to make that work, we need to implement getProperty. Like that. And I need to add about 3 lines of code here, and that test will be passing. So let me fill this in, then we'll back up and talk about what this is in just a moment. All right, we'll do that. And in here, I simply want to retrieve the value in the map that's associated with that key. All right, we'll come back to that code momentarily. Let's run the test and make sure that it passes. And it did. We got a green bar there. So let's take a closer look. So on line 5, I'm simply declaring a protected property called dynamic properties. And I could have called that anything. That's not a special property name for Groovy's. It's not a special name. I could have called it anything. It's just a protected field in this class called dynamic properties. And I'm initializing it to be an empty map. Right? Groovy has a literal syntax for creating maps, and that's how you create an empty map. So I've got an empty map called dynamic properties in this class. So anytime set property is called, what I'm doing is I'm putting a new entry in the map where the key is the name of the property that is being assigned a value, and the value associated with that key is whatever value is being assigned to that property. So when I said ex.company name equals OCI, property name is company name and value is OCI. So I'm simply putting those things in the map. And then later, when I try to retrieve the value of the company name, this is returning, remember that return statements are optional in Groovy. This is returning the value in the map that is associated with the key company name or favorite language, whatever the name of the property that I'm retrieving the value of. Right? So with just those, depending on what we're counting, there's really just 3 lines of code there. With that, we've got at least some of the behavior that the real Expando supports implemented. And that is I can make up properties and assign them values, and I can retrieve the values of those properties, and I'll get back the value that I expect there. So questions about any of that so far? That's good. All right. Let's write another test. It will look something like this. Right, so that closure accepts 3 parameters and simply returns their sum. And we'll say 100 is equal to ex.addNumbers. Is that right? Yeah, that looks right. So let's run that test, and I expect it to fail, and it should fail at line 24, and it did. Right, so if we look at the stack trace here, line 24 is where the error happened. This line works for the same reasons that lines 10 and 11 work. All I'm doing at line 21 is I'm making up a property that doesn't exist, and I'm assigning it a value. We've already accounted for that, right? So that's simply calling set property, and the first argument to set property is the string addNumbers, and the second argument to set property is this closure. Remember that I said a closure is a real object that can be passed around the JVM. So the second argument to that set property method is the closure itself. This is where the problem is coming up, and the exception that I got here is a missing method exception. So in general, when you invoke a method that does not exist, Groovy will throw a missing method exception, and that's what's happened here. So the last piece of the puzzle here is I need to implement a method missing method. We'll start with that. And so we'll run this. The test is still going to fail, but it's going to fail in a different way now. There we go. We got the value assertion failed. We expected ex.addNumbers to return 100, but it in fact returned null. what's happening is that call to ex.addNumbers is resulting in this being called, and this isn't returning anything. It's as if we had done this, right? So null is being returned from that method call. We need to add just 2 or 3 more lines of code here to make this work. So I'll fill this in, and then we'll back up and talk about what's going on here. All right, let's run our test, and I'll come back to that code in just a minute. Let's see the test pass. And it did pass. We got green bars. So all of these assertions are passing now. So when I called ex.addNumbers and passed in 35, 25, and 40, we really did get 100 back. So let's figure out how that works. So I'm invoking a method that does not exist on an instance of the Devoxx expando class. So Groovy steps through a series of things trying to handle that method call, and they all failed. There is no real method here called addNumbers, and any of the other techniques that I might have used to add such a method to this class, none of those exist. So we're kind of at the end of the line, and Groovy is just about to throw a missing method exception. But one of the last things Groovy's going to do is it's going to check to see if this method exists. And if it does, Groovy's going to invoke this method. And the first argument will be the name of the method that was called, so addNumbers in this case. And the second argument is really this. You don't have to statically type it, but it's an array that includes all of the arguments that were passed to the method. So that will be the numbers 35, 25, and 40, or whatever I've got in the test there. So on line 16, I'm retrieving the value from the map that is associated with the key addNumbers, right? Method name is addNumbers. And here I'm checking to see if that value exists and if it is a closure. And if both of those are true, if it does exist and it's a closure, then I want to invoke the closure and return, I want to return whatever the closure returns. And when I invoke the closure, I need to pass these arguments into the closure. And the asterisk in this context is the spread operator, and that's effectively as if I had done this. I said prop arg sub 0, arg sub 1, arg sub 2, right? The closure doesn't accept an array of objects. It accepts 3 separate objects. I called the variables A, B, and C. These are the parameters into the closure, A, B, and C. What's going on right here is I need to pass not the array, but individual elements that are in the array as an argument into the closure. So if I only wanted to support closures that have 3 parameters, then this would work, but that's not very flexible. What's going on right here, the spread operator in this context can be applied to a collection or an array, and the way that works is when Groovy invokes this closure, it will pull the individual elements out of the args array and pass each of them as discrete parameters into whatever's being invoked here. In this case, it's a closure, but if I were invoking a method, the exact same syntax would do the same thing. So when you've got a collection of things and you want to pass the individual elements that are in the collection as discrete arguments into a closure or into a method, Groovy's spread operator, the asterisk operator there, makes that very simple. So all that makes sense?
Jeff,
yes. Go ahead.
In case the instance of the check will not pass, what will that missing return?
Yeah, the question is, if the instance of check does not pass, what will this method return? And it's going to return null. It's as if we fell down here and did that. So let's write another test that describes is not a closure. Let's do this. And we'll say ex.sum equals 9. Right, we want to we want to decide what happens when I invoke a method and the value isn't a closure. Right up here, the value of the addNumbers property is this closure. And down here, this is nonsensical. So we need to decide how that's supposed to behave. Maybe what I want to do is I want to throw a missing method exception. So as the author of the class, we get to decide how the thing's going to behave. That's what I expect to happen, or that's what I want to happen, I should say. So we'll run the test, and that's not what happened. We expected a missing method exception to be thrown, but it wasn't. So maybe what I want to do here is throw a missing method exception like that, and run our test again. I need to pass the correct arguments to the missing method exception. It's method name, the class type, and then the arguments. That's what it is. So method name, Devoxx, expando, and args. I think that'll work. I am missing the new operator. Good catch. We're pair programming, and I've got 212 pairs right now. There we go. We got a green bar. So I get to decide as the author of the Devoxx expando class how I want the thing to behave when you do something like this. This is nonsensical. I could throw an illegal state exception. I get to decide how the thing's going to behave. And the decision that I just now made is that if I try to invoke a method and the value that method has, the value of the corresponding property is not a closure, then I want to throw a missing method exception. Maybe we could have an else block here that says if the property is not null and it's not a closure, so it's some other value, then throw an illegal state exception or something that describes, hey, this is not a closure, it's an integer, you're not allowed to do that. But as the author of this method, I get to decide how the thing behaves. Does all that make sense? Any other comments about any of that code? Yes?
If we had a company name property with a setter specific, would it be called before the set property name default?
The question, I think, is if you're assigning a value to a property and there is a real property with that name, how is the expando class going to behave? And the way that it's written right now is if there was a real set company name method, that would be called. There's another way to go about this where instead of set property, you can do this. Property name value. That one, this behaves a lot like set property, except it will only be called when you assign a value to a property that does not exist. So again, as the author of the Devoxx expando class, I get to decide, do I want this special dynamic property behavior only when the property doesn't exist, or do I want it for all? Do I want to intercept all property access? And the way that it's written right now, I'm intercepting all property access, which it turns out is reasonable. There's no reason to ever assign a value to a real property in the expando class. So that's the behavior that's implemented there. Does that make sense? Yeah, so there are two, I should clarify that as well. There are two versions of property missing. One that looks like this, and another that looks like this. All right, that just accepts a string. This will be called when you retrieve the value of a property that doesn't exist, and this will be called when you assign a value to a property that doesn't exist. Right? Good question. Any other comments before I press on? That's good. All right. Very good. So again, quickly, before I jump back in the slides, just to review, the amount of code we've got is maybe 8 or 10 lines of code. There's not a whole lot of code there. And we've pretty much duplicated, recreated the behavior of the real expando class. The real expando class has some more details in it for some error handling and some other behavior, but for the most part, we've mostly recreated the behavior of the real expando class with very, very little code. Right? And all of that, what we're really doing with all of that is we're tapping into Groovy's dynamic dispatch mechanism. We're telling Groovy, hey, I'm writing a class, and anytime someone retrieves a value from or assigns a value to a property on an instance of this class, I'm writing the code that wants to participate in that access. Right? Anytime someone retrieves a value of a property, I get to decide what to do, and anytime someone assigns a value to a property, I get to decide what to do. So in our case, we've simply got values in a map, and we're not doing anything terribly interesting. But inside of the getProperty method, we could do whatever we have. There can be as much complexity or interesting behavior in there as you like. What's important, again, is that Groovy's provided a mechanism for you to write code that participates in that property access, property assignment, and method invocation process. Right? Groovy makes it very, very easy to tap into that process and participate. All right, so let's press on and talk about closures. Closures are a really, really important and powerful feature of the language. Sure, I've got this in a healthy state. There we go. That looks good. So let's. I want to write a little bit of code to just tinker with some closures and get an idea of some of their capabilities. Then we're going to back up and talk about closure delegates and how they relate to metaprogramming. So here I'm going to say C equals that. Right. So that's a closure, and the closure simply calls println and passes the closure is running as an argument. If I run this program, nothing interesting is going to happen. It just ran and there is no output down there because all I've done is I've defined a closure that has some behavior in it, but I've not invoked the closure, right? So if I do that, now we'll see some output down here. So you see the closure is running, right? And if I were to invoke the closure over and over again and run the program, we'll see the behavior that you'd expect, right? The closure is running 3 times there. All right, so a closure is a block of code. It has some things in common with methods, but it's also really quite different than methods. One of the things that is interesting about closures is closures are first-class objects. It's a real object on the heap. Here we've got a reference that points to that object. The reference is called C. I can invoke methods on C. I can retrieve and assign values to properties on C. The closure really is a real object. Just as if you'd written the person class and you created an instance of the person class, that's a real object. The closure is a real object. It's not just some syntax. It's a real thing on the heap. So let's do this. If I were to do that, right, and invoke the closure. When I run this, we're going to get a missing method exception, right? Missing method exception, no such method demo.append. So on lines 2 and line 3, we never even got to line 3 because line 2 threw an exception, but both of those lines of code are attempting to invoke a method called append, right? In Groovy, when you're passing arguments to a method, the parens are optional. I can put them here to make it look more like a method call, but it's a method call even without the parens, right? So line 2 is invoking a method called append and passing a string as an argument, the string Jeff. And then line 3 is going to do the same thing if line 2 succeeds. But there is no method called append here, so we're getting a missing method exception. So let's do this. All right, let's run this and see what we get. So if we look at the output down here, that says the value of the string buffer is Jeff is in Antwerp, right? That's the value of the string buffer. If we look at, start at line 6. On line 6, I'm creating an instance, a new instance of the string buffer class. So now there's a string buffer object. And line 7 is really the interesting part of this. I'm assigning that string buffer to be the delegate for this closure. So there are a couple of other properties we're going to look at in the closure class. This is the first of 3. Every closure has a delegate associated with it. Every closure has one delegate associated with it. And that delegate gets an opportunity to respond to method calls that are made inside of the closure. So when the closure is executing, when we get down to line 8 and invoke the closure, Groovy is going to go through some steps and then eventually get up to executing the line of code at line 2. And what line 2 is doing is invoking a method called append and passing a string as a parameter. And Groovy is going to look in the context where this code is. This happens to be in a script, but let's say that it was in a class. Groovy is going to look around in that class for an append method that accepts a string as a parameter. And there is no such method, so Groovy is going to throw a missing method exception, potentially. But another thing Groovy is going to do before throwing a missing method exception is it's going to interrogate the closure's delegate and ask the delegate if it could respond to a method called append if a string was passed as an argument. And in this case, the string buffer class can, in fact, respond to that method call. There's an append method in the string buffer class that accepts a string as a parameter. So instead of throwing a missing method exception, Groovy is going to invoke the append method on the delegate. In this case, it's going to invoke the append method on the string buffer. So no exception is thrown. And then we get down to line 3 and the same thing happens. So every closure has a delegate associated with it, and the delegate gets an opportunity to respond to method calls that are made inside of the closure. Remember that. That's just one piece of the puzzle here. We're going to put several pieces together and learn how a lot of this really works. So that's not what I wanted. Let's go out here. I want to do the same sort of thing in a real class, not as opposed to in a script. So let's do this. Create a new Groovy class called Closure Demo. And we'll put a method in here called run. And I'm just going to copy some of this code. And we'll see in a moment why I want this to be inside of a class. All right, so if I run this class now, we should see basically the same behavior. We should see the same behavior. And that's what happened. We see Jeff is in Antwerp down there. But let's do this. Let's add a method here called append that accepts a string parameter. Like that. Now the question is, when lines 11 and 12 execute, what's going to happen, right? So there's at least a few reasonable possibilities. Maybe line 11 is going to invoke the method defined at line 5. Maybe line 11 is going to invoke the append method on the string buffer. Maybe they'll both get executed. Or maybe Groovy will throw some sort of ambiguous method exception because it doesn't know what to do with line 11. There are two different places that the append method could be handled. And so maybe Groovy's going to throw an exception that says, hey, you can't do that. So let's run this, and we'll see that in fact what happens is the method up at line 5 is being invoked, and the string buffer is empty. So when line 11 was executed, that's calling the append method defined at line 5. You see the output there that suggests that. The same thing happens when line 12 executes. And then when we get down to line 19 and print the value of the string buffer, it's empty because we never interacted with the string buffer. So it looks like the delegate only gets an opportunity to participate when a method call is made, when a call is made to a method that does not exist, right? So when the append method does not exist in this class, the string buffer's append method gets invoked. And when the append method does exist in this class, it gets invoked and not the string buffer. So it looks like the delegate only gets to respond if the method doesn't exist. And that's true, kind of true and kind of not true. So there's another property in the closure class called owner. And it's a read-only property, so you can't do this. But it's as if you did that immediately after creating. Anytime you create a closure, the owner is always the thing that created it. So it's as if you did this. You can't do that. It's a read-only property. But the owner of the closure is always the thing that created it, right? So we see that there are two things here. There's the delegate and the owner. And it turns out that each of them potentially gets an opportunity to respond to method calls that are made when the closure is running. And there's a third property that we need to talk about called resolve strategy. That is, it can have a value like that. So what that says is when the Groovy runtime is resolving method calls that are made inside of the closure, the strategy that I want to use is owner first. And that means Groovy should first check to see if the owner can respond to the method. And if the owner can, then do that. And if the owner cannot respond to the method call, then go interrogate the delegate. It turns out that the default resolve strategy is owner first. But if we change the resolve strategy to delegate first, we'll see different behavior now. We'll see that now the string buffer is going to be interacted with. There we go. The string buffer is Jeff is in Antwerp. So the default value for the resolve strategy is owner first. And if you remember that every closure has a delegate and every closure has an owner. Just remember delegate and owner. If you can remember that, then you can remember, you can easily remember the 4 possible values for the resolve strategy. And this is what they are. Right? So the 4 possible values for the resolve strategy are delegate first, owner first, delegate only, or owner only. Delegate first means the delegate gets the first opportunity to respond to method calls, and only if that fails does the owner get interrogated. Owner first is the other way around, and owner first is the default. Right? I'll put that up at the top to highlight that. Owner first is the default. That's what happens if you don't assign a value to the resolve strategy. Delegate only says that the Groovy runtime will interrogate the delegate and give it an opportunity to respond to the method call. And if that works, fine, then we're finished. And if that doesn't work, then we'll get an exception. The owner will never be interrogated if the resolve strategy is delegate only. Delegate only says only the delegate gets an opportunity to respond to method calls. And owner only is the same thing, but only the owner gets to respond to method calls. So I'm going to comment those out. So the default resolve strategy is owner first. And that's why when I run this right now, the method up at line 5 is what's being executed. Right? The append method was called twice there. And if I set the resolve strategy to delegate first, that's when we'll see different behavior. Right? Now the string buffer has a value, and the method at line 5 was never executed. So every closure has a delegate and an owner. Those 2 things potentially get an opportunity to respond to method calls that are made when the closure is executing. And the resolve strategy dictates which one gets interrogated first and indicates whether or not there is a second one. So if the resolve strategy is delegate only, then that's all there is to it. Only the delegate gets to respond to method calls, and if that fails, then we'll get an exception. Right? Does that make sense? Questions or comments about any of that? Good. So let's figure out how that's why that's useful. So this is basically what I just demonstrated. So the closure at the top is invoking the append method a couple of times. There is no append method, so we'll get an exception. And the code at the bottom is assigning a string buffer to the closure's delegate to be the closure delegate. And in that case, the string buffer gets to respond to those method calls. Those of you who have done Grails development probably recognize this, right? So in a Grails application, you can declare a domain class, and the domain class can have any number of properties, persistent properties like login, password, email, and age in this case. And then in your domain class, you get to declaratively define some rules for what are valid values for persistent properties in this domain class. So for example, what's expressed here is that the login property has to have at least 5 characters and can have no more than 15 characters. It can't be blank, and it has to be unique. We can't have 2 users with the same login name. The password has to be at least 5 characters and no more than 15 characters and cannot be blank, and so forth. So we've got a DSL for describing constraints that dictate what are valid values for your persistent properties. And if we look at the code inside of that closure, the very first line in the closure, what it's doing is invoking a method called login and passing a map as a parameter. The map in this case has 3 entries in it. The length, the blank, and the unique are all keys in the map. There is no login method in this class, right? So what Grails is doing at application bootstrap time, so early on in the application startup procedure, Grails knows how to locate all of your domain classes. So it does that. Now it's got this list of classes, and all those classes are domain classes. One of the things Grails is going to do is iterate through all of those classes and look to see if this constraints property exists. And if it does, Grails is going to grab the value of this constraints property, grab that closure, and execute it. But if that's all the framework was doing, then the first line inside of this closure would throw a missing method exception because there is no login method. So that would result in an exception. So what's happening is Grails is grabbing that closure and creating an instance of some class whose name you don't care about. It's a class that's inside the core of Grails. And that class has a method missing method in it, right? So we've seen how method missing works. If a class has a method missing method in it, you can create an instance of that class and invoke any method at all, and that will go to the method missing method instead of a missing method exception being thrown. So the delegate that's being assigned to this closure, and again, this is all happening in the framework. It's not something that you have to deal with from the application developer's perspective. The framework is assigning a delegate to this closure, and the delegate has a method missing in it, and then the closure is executed. So when that first line of code gets invoked, we're invoking the login method and passing a map. What the method missing in that delegate is going to do is look at the method name, login, and it will go verify that there is a property in this class called login, and there is. So then the method missing will look at the map and go through all the entries in the map and do a bunch of stuff to configure the Hibernate session factory, and there are a number of places where these constraints come into play. But basically all the moving parts, the machinery necessary to make that possible are the things that I just described, right? We see how to intercept calls to methods that don't exist with a method missing method, and we've seen the role that a delegate plays when a closure is invoking methods, whether they exist or not exist or don't exist. So all the pieces of the framework that make this possible, we just covered in the couple of simple examples that I wrote. So what I'm about to describe doesn't exist, but it would be easy to create. Someone could write a plugin for Grails that would go through all of the domain classes and grab this closure and assign a different delegate to the closure and execute the closure. And maybe what that delegate does is intercepts these method calls, and instead of configuring the Hibernate session factory and doing all the stuff that the real delegate does, maybe this delegate intercepts these method calls and creates documentation. Right? You could have HTML or PDF documentation for the constraints that are defined in all of your domain classes. So if we did that, we'd have a situation where this exact same block of code, the code that you're looking at here on the slide, inside of that constraints closure, that exact same block of code can be executed in two different contexts, one in the running application and one in this documentation generator thing. And that same block of code could have fundamentally different side effects, right? In the running application, calling login and passing a map does stuff with Hibernate. And in the context of the documentation tool, that exact same line of code causes something else to happen. Maybe another row gets put in an HTML table or something. So we've got a DSL here that describes what are valid values for persistent properties in a domain class, and it's up to the delegate to basically be the interpreter for the DSL, right? The delegate gets to intercept these method calls and do whatever needs to happen in response to those method calls. So all that makes sense? Good. So Groovy provides this class called Markup Builder, and the Markup Builder is a really simple way to create markup. So let's do this. We'll say mkp equals new groovy.xml markup builder, and we'll say mkp.sports. All right, and then we need another sport down here. That's good enough. All right, so if I run this now, we'll see what we get here is, so some XML was just created, some markup was created, and the root element is sports, and then there's a child element of that called baseball, and a child element of that called teams, and you can see the structure of this markup is consistent with the code that you see up above. So the markup builder is a super simple, super slick way for generating markup from Groovy. And again, the mechanisms that we just talked about make that possible, right? So on line 3, what we're doing is we're invoking a method that doesn't exist. We're invoking a method called sports. And the markup builder is intercepting that method call because there's a method missing method in the markup builder. And what that method missing method is doing is looking at the method name, sports, and creating an element, an XML element, right, whose name is sports. And then the markup builder's method missing method is invoking the closure that's being passed as an argument, right? This is the argument to the sports method. It's invoking that closure, but before invoking the closure, the method missing method in the markup builder has to set the delegate of that closure to be this, meaning the markup builder itself. So as the nesting happens, when this call to baseball happens, that will be intercepted by the same method missing that intercepted this sports call, and likewise teams and on down the line. It can be nested arbitrarily deep. So there's a certain amount of complexity in the markup builder class to tie all that together and make it work, but that complexity does not leak through back to here, right? So the result is we end up with this really simple mechanism for dynamically generating markup, and Groovy's dynamic dispatch mechanism is what's making all that possible. Right. Make sense? All right. So here's another example of that right here where it looks like we're generating some HTML. So the root element happens to be HTML. So all the bold text here, those are all calls to methods that don't exist. And the markup builder is intercepting those method calls and creating markup that looks something like this. Right? Could barely be more simple. All right, let's talk about the expando meta class. So first, I want to run this program and find out what kind of object name points to, and it's a java.lang.string. It's not a special Groovy string, or it's just a standard Java string, java.lang.string. So if I were to invoke a method like name.doSomething, there is no doSomething method in the java.lang.string class, so that's going to throw a missing method exception. And it did. Missing method exception, no method doSomething found on the string class, right? But I can add a doSomething method to the string class using the expando meta class. All right, so let's run that. There we go, and the output there says in the doSomething method, so that worked. So from Groovy's perspective, every class has a meta class associated with it. So it's not the case that this only applies to Groovy classes. From Groovy's perspective, every class has a meta class, including Java classes and Groovy classes and Scala classes and Clojure classes. Every class has a meta class associated with it from Groovy's perspective. So a way to reference a class's meta class is what you see there. So string.metaclass evaluates to the meta class that's associated with the string class, of course. And the meta class is what the name suggests. It's information about the class. So the meta class, string.metaclass contains information about the string class. So there are things I could interrogate on that meta class, like I could discover all the methods that are defined in the string class. I can discover details about the string class. But what I want to focus on is not discovering information about the string class, but adding information to the string class. So when I use a syntax like this, what that's doing is that's adding a method called doSomething to the string class. Not to a particular string, but to the string class. So now all instances of the string class have a method on them called doSomething, and this is what that method does. So now I've added a method to the string class, right? And that applies to all strings, including strings that are created in the future, right? So if I do this, that works. And as we saw before, it applies to strings that already exist. So when line 1 executes, I'm creating an instance of the string class, and the doSomething method does not yet exist. Then later that method is added, and now I can invoke that method on an object that was created before this ever even happened. Right? That'll still work.
Could you call this method from Java?
Yeah, the question is, could you call this method from Java? So practically, no. You can, but you have to do some tedious stuff. You're calling into the Groovy runtime that says, here's an object and here's a method name. You can't, practically speaking, the answer is no. You can't call it from Java. The Java compiler is, when you make a method call, like this line of code right here, in Java code, the Java compiler will look at this reference, the name reference, and figure out what type it is, and the compiler makes sure that this method exists, right? And the code won't compile if the method doesn't exist. So that's fundamentally why you can't call the do something method from Java, because you can't compile the Java code that's going to try to call it. As I said before, the Groovy compiler is generating something fundamentally different for this. A consequence of that is when let's say you're not doing metaprogramming, you're just, let's say you've got a string buffer and you intended to call sb.append hello world, right? But you made a typo here, and maybe you've got an extra p, right? So that's going to be a runtime problem. Line 12 is going to be a runtime problem. It's not a compile time problem. It's a runtime problem. And some folks are a little put off by that. It seems like maybe a bug in the compiler. It's not a bug in the compiler. It's important that you're allowed to call methods that don't exist in a dynamically dispatched language like Groovy. It's important that you're allowed to invoke methods that don't exist. But it's also one of the costs of all the great benefits that come from that is you don't get the same kind of compile time, type checking, and feedback that you get with a language like Java. But stand by on that. I'm going to talk more about that later on when we get into compile time metaprogramming. We can get in a situation where this code will not compile. If what I really want is static type checking, I can rig things up such that this code won't compile. But that's getting a little ahead of ourselves. But in short, the answer to can you call the do something method from Java is no, you cannot. Other comments about any of that? All right, very good. So what is this example doing? This example is adding a method called vowels to the string class, and it's going to return a list of characters that is all the vowels that are in the string. So if I start with the string Groovy is a great language, and I invoke the vowels method on that string, then I'll get back the list of vowels that you see there. All of the vowels that are in the string that I started with. Another way to add dynamic methods to classes in Groovy is with Groovy's really slick extension methods mechanism. So if you have a file at metainf/services/org.codehouse.groovy.runtime.extension module, right? The name that you see there. So that's the name of a file, org.codehouse.groovy.runtime.extension module. In that file, you can have text like you see here. Let's create that file. There, I've already got it here. So I've got a file called that has that name. In my project, it's under source main resources metainf/services. So the file name is org.codehouse.groovy.runtime.extension module. The module has to have a name. It has to have a version, and this extension classes, in this case I've only got one thing here, but I could have, this is a comma separated list, right? So I can have as many extension classes as I like here. We're only going to need one. So that looks like I want a class called devoxx.demo.stringExtensions. That's this guy right here. So if I were to define a static method like that. So the way to define extension methods is you've got to have this descriptor that describes your extension method classes, right? So devoxx.demo.stringExtensions is our extension method class. Inside of the extension method class, declare static methods, not instance methods, but static methods. And the way this works is, for the most part, the method signature is like any other method. You declare a return type and declare the name of the method. The first argument, the methods all have to have at least one argument. And the first argument indicates the type that you want this method added to. So if I run a program with this string extension class in place, what's going to happen is a method called getMagicNumber is going to be added to the string class, and this is the implementation of the method. It's simply going to return the number 42. So let's verify that works. All right, let's run that. Looks like it worked. We got a green bar. Let's change this number just so we see a failing test here. There we go. So now we'll make this pass. That worked. What if I did that? Right, because of Groovy's, the way Groovy's property access works, I can retrieve the value of the magic number property, and Groovy will invoke the getMagicNumber method for me. So the pieces of the puzzle again are you have to have this descriptor with the long funky name, org.codehouse.groovy, so forth. Inside the descriptor, you've got to have a module name, a module version, and then you can have, remember this is a comma-separated list of classes. Groovy will find all of those extension module descriptors that are on your class path at runtime, and it will load up all of these extension classes like this. And I could define any number of methods here. Right, and all of these methods, they don't have to be for the same type, right? I can do that. And now I'm defining a method that's going to be added to the integer class. If the method accepts parameters, the way to do that is what you see here. So the method in the extension method class has 3 arguments: string, integer, and integer, right? Or I'm sorry, integer, integer, and integer. But the do something method that you can invoke actually only accepts 2 parameters, right? These are the parameters that you can pass into the do something method. The first parameter in the declaration here tells Groovy what type to add the method to, and when you invoke the method, the instance that you invoke the method on will be passed in as the first argument. So let's make this, instead of simply returning 2112, we can say instance.size, right? So we'll make magic number be the size of the string that you invoked it on. So that should be 4, that should be 4, and that should be 5. And that worked. All those, that's green bars, right? So the first argument in the method declaration indicates the type that the method will be added to, and when the method is invoked, the object that you invoke the method on will be passed as the first argument. And if the method accepts parameters, then the way to express that is like that. So we'll do this. So now I need to pass 1 argument to the getMagicNumber method, and that's a multiplier. And what the getMagicNumber method is going to do is multiply the number of characters in the string by that multiplier. So now if we come over here, we're not going to be able to do the property thing anymore because it's no longer a property. So let's see, if we make that 3, this will be 15. If we make this 2, that'll be 8. And if we make this 5, that'll be 20, right? So now I'm passing just 1 argument to the getMagicNumber method, and that 1 argument is passed in as the second argument to the method. Does that make sense? The first argument is the instance that you invoke the method on, and then every argument after that are actual arguments that need to be passed when the method is invoked. Does all that make sense? So with that, you get a lot of the same kind of flexibility and interesting capabilities that Expando Metaclass has to offer, but it's more simple. This is tedious. There are a number of challenges with doing the Expando Metaclass approach. One is, where do you do this? This needs to happen early on in your application bootstrap process. You need to make sure that it happens before any code tries to invoke the method, and that can be, you can get in situations where that's more challenging than it seems like it might be. But orchestrating where that, or making sure that the meta class stuff happens early on in the application lifecycle is important. Also, it can be hard to tell where these methods are coming from. So you know that there's a do something method in your project, and someplace there's code that's doing this, but maybe you're not sure where that is. The extension module approach simplifies or cleans up some of that, not all of it, but cleans up some of that. It certainly addresses the lifecycle part of the problem, because all the extension module stuff will be executed before any of your code gets executed. So you don't have to worry about making sure that this happens before this happens, right? You can't get things out of order when you're using extension modules. Early on, when Groovy is initializing itself, all the extension methods will be put in place. But there are times when extension methods won't work. So one of the limitations of using extension methods is you have to know the name of the method. In this case, it's getMagicNumber. You have to know the name of the method at compile time. There are scenarios where you might want to generate methods dynamically at runtime, and you don't know the name of the method until you gather some information at runtime. Dynamic finders are a good example inside of Grails. Right, so inside of Grails, if you had a domain class called person, and you had properties like first name and last name, like that, Grails will create dynamic finders like find all by first name Jeff. And this will send a query to the database that retrieves all the person instances whose first name is Jeff. There'd be no good way to write extension methods that cause the find all by first name method to be added to the person class, because we don't even know that the person class exists when we author the framework, right? You're going to write the person class, and there's no way to know what properties are going to be in the person class. So there's metaprogramming that happens inside the framework that does something like this, that will say person.metaclass.methodMissing equals method name and args. Right, something like that. And then in here, we do all the dynamic finder stuff to create the query and go to the database. But there's no good way. That really has to be done using the expando metaclass approach, or at least it has to be done using method missing. That's an example of something that could not be dealt with using extension methods, because we don't know the name of the method ahead of time. So it's not the case that extension methods are necessarily better than the expando metaclass approach, and it's not the case that the expando metaclass approach is necessarily better or worse than some of the other techniques we're going to talk about in the second half of this. What you want to do is to gain an understanding of how these things work, and if you understand how they work, you'll understand where to apply the different techniques. And we've only seen a few of them so far. We're going to get into more in the second half here. So all we've seen so far, or what we've seen so far, are some really powerful and really flexible mechanisms that Groovy provides for you to tap into Groovy's dynamic dispatch mechanism. You get to intercept calls to methods. You get to intercept calls to methods that don't exist. Likewise, you get to intercept property access. The closure delegate stuff is relevant to building DSLs, as I described earlier. So so all we've seen so far is the runtime metaprogramming capabilities that Groovy has to offer, and now I'm going to get into the compile time stuff, but I'll take a break before we do that. Before we take a break, can I address any questions or comments about any of the runtime metaprogramming stuff? Everything good? All right, let's take, what is it right now? It's quarter till. Let's take a 10-minute break, and at 5 till, we'll press on with the compile time stuff. All right, let's pick back up. There's one more piece of the runtime stuff that I want to talk about before I get into the compile time metaprogramming. So let's just do that. So I've got a class called widget here, and I'm going to add a method missing method to that class like that. So imagine the widget class is, I'm not authoring the widget class. That's a class someone else wrote, and I want to add some behavior to the widget class. So this is off someplace else, and I'm decorating that class with some new behavior. So I want to add a method missing method to the class at runtime. Like that. So now if I were to create an instance of the widget class, right, I can invoke methods like 1 and 2. There we go. That looks like that worked. Right, so we see in method missing for method 1, 1, 2, 2, 2, 2, 2. Right, so every time I invoke one of those methods, when lines 9 through 15 are executed, the method missing that I've dynamically added to the widget class is being used to intercept those method calls. So I mentioned Grail's dynamic finders earlier. So you can call methods like person.findAll by first name, find all by first name and last name, find all by age greater than. There's all kinds of combinations of interesting things you can express in dynamic finder method names. And this is fundamentally how that's happening inside the framework, right? So you wrote the widget class, you wrote some domain class, and then at runtime, Grails is adding a method missing to your domain classes, and that's what allows you to invoke methods that don't exist, like find all by first name. And inside the method missing, we parse the method name and figure out what you're trying to express and turn that into a query and so forth. So what we see here is an example of dynamically adding a method missing to a class at runtime. And remember that method missing is kind of at the end of the line, right? So when I invoke the one method, there are a number of places that method might be handled. Maybe there's a one method in the widget class. If not, maybe there's a one method that widget inherited from java.lang.object, or maybe someone added a one method using something like this. Metaclass.one equals that, right? So there are a number of places that the one method might be handled. And at the end of the line, before throwing a missing method exception, Groovy will check to see if there's a method missing method attached to that class. And there are really powerful and useful ways or reasons to take advantage of method missing, but it's sort of the least performant option, right? It's at the end of the line. It's the least performant option for responding to a method call. But there are times when that's the thing that makes the most sense, like dynamic finders and Grails. We have to add the method missing at runtime. We don't want you to have to author that in your class. And it's just what I said, that it's kind of the least performant way to respond to a method, but there's a simple thing you can do to sort of bite into the performance cost there. So let's have this method return something. I'm just going to have it return the uppercase version of whatever the method name is. So we want to print that out. All right. Maybe I don't need so many of those. All right. So I'm going to print out the return value from each of those method calls, and they should be the uppercase 1 and 2, right? And notice what's happening is, so right there, so I invoked the one method. We see in method missing for 1, and then we see the uppercase 1. In method missing for method 1, then the uppercase 1. So every time I invoke the method, we see 2 pieces of output. One is a piece of output that's coming from the method missing method, and the other is the output that's being generated down here where I'm just printing the return value. And I want to see both of those because, well, the reason I want to see both of those will become clear in a minute. So there's a simple thing that I can do now to potentially significantly optimize this. So what I want to do is I want to put this code inside of a closure like that, and then invoke the closure. So we should see the same behavior so far. If I run the program, there we go. So we see the same behavior, in method missing for 1 and so forth, but with just one more line of code, I can do something interesting here. I can say widget.metaclass.methodName equals C. So let's see the result of that, and then I'll talk about what's going on there. Here's the interesting bit, is notice that method missing was only executed once for the one method and once for the two method. Right? And you see that? So I can invoke the two method a million times, and I'll never have to go back to method missing again for that particular method. So what's happening on line 10 is I'm adding a method to the widget class whose name is this, right? mn is the first argument here. That's the name of the method that was invoked. So when line 16 executes, Groovy figures out that there is no one method. So Groovy is going to invoke the method missing for the one method. mn will be 1 and args will be an empty array. So we've invoked a method that doesn't exist. So we create a closure that represents how I want to respond to that method. I simply want to return the uppercase version of the method name. But whatever complexity needs to be in that closure can be in that closure. And then this is the interesting bit, right? That's adding a method to the widget class whose name is 1, and the closure that represents the implementation of that method is this closure. So the first time that I invoke the one method, method missing has to be involved, and now I can invoke the one method over and over and over again, and the method missing method is never involved again until I invoke a different method, like the two method. And then if I went back to invoking the one method, right, we will not have to invoke method missing again for that. Method missing is only going to be invoked once for each of the dynamic methods. So we see it here at the top. We see invoking method missing for 1, method missing for 2, and then as I carry on, we never execute method missing again for either one of those, right? So the pattern that's implemented here is known as intercept, cache, and invoke. Intercept, cache, and invoke. So by having the method missing here, we're intercepting that call to a method that doesn't exist. This is where we're caching it, right? We're caching the implementation of that method onto the meta class. And then this is where we're invoking the method, right? We're invoking the closure, which invokes the block of code that represents how we want to respond to this method call. So again, just with just this line right here, right? Line 10 is the interesting bit. What we've done is enabled the program to take advantage of the power and flexibility that method missing has to offer, and we've subtracted some of the cost that we have to pay to get there, right? So the first invocation of 1 is going to be potentially slower than every subsequent invocation, but it's only a missing method the first time, right? Because the first time that we invoke the one method, we end up doing that. So now it's no longer a missing method. It's a method that does exist. It's a method that's been added to the widget's meta class. Does that make sense? Any comments about any of that? All right. Let's talk about some really slick compile time stuff we can do. So let's start by looking at a spec here. So we're going to do some more test-driven development, and I'm going to create a class called foo. And I've already got a thing in place. I've got an annotation called magic number, and this is the annotation. There's nothing interesting in the annotation yet. It's a source level annotation that can be applied to a type, and the annotation is called magic number. There's really nothing interesting in the annotation yet. So I want to be able to annotate this class with magic number. And what I expect, or what I want to happen when I annotate a class with magic number, is I want the class to end up with a method like this. Right? But I don't want to have to author that method. Maybe there's lots of complexity in the method, but I don't want the author of the foo class to have to write this code. I want them to just annotate the class with magic number, and then at compile time, I want that to result in a method being added to this class called getMagicNumber. What do I want to do here? We'll just say, given the new foo, right? That's the way I want the thing to behave. If I create an instance of foo and then retrieve the magic number property, I expect the value of that to be 42. And we can shorten this, I guess. We'll just do this. Right? I expect the magic number property to be 42. If I run this test right now, it's not going to pass. we should get a missing property exception at line 12. And that is what happened. Right there, we see missing property exception, no such property, magic number at line 12. This right here is what's causing the problem. So I've annotated the foo class with @magic number. The magic number annotation looks like that. And what I want to do is I want to write an AST transformation. So Groovy provides a mechanism called AST transformations. And what an AST transformation is, what it is a thing that gets to transform the AST. So when Groovy is compiling your source code, it's parsing your source files, your .groovy files, which is just a bunch of character sequences, whatever you've typed in your source files. Groovy has to parse your source files and create sort of a model in memory that represents what you've described in your source files. And that model is called an abstract syntax tree. That's what AST stands for. So the compiler is creating this tree, this model in memory that represents whatever it is you've expressed in your source code. And an AST transformation gets to transform that model, right? It gets to mutate, gets to change that model that the compiler created. So what we want to do is we want to write an AST transformation that will be applied to any class that's annotated with the @magic number annotation. And what we want that AST transformation to do is add a method to the class that was annotated and have the method be called getMagicNumber and have it return the number 42 for now. So let's take a look at that. So we want to look at, I've got a class called magic number transformation, and I'm going to have this thing implement AST transformation. And by the way, when I'm done here, this project that I'm working in is all in Git, and I'll push it to a GitHub repo, and I'll show you where that is. You'll be able to access a copy of all this code if you're interested in that. Let's see, I've got to spell implements correctly. All right, I need this to be like that. All right, so I've annotated this class with Groovy AST transformation, and I've expressed that this class implements AST transformation. And so anytime this transformation, the way that the compiler interacts with this transformation is it will call this visit method and pass a couple of things as arguments. The first thing that's passed as an argument, the first argument that's passed into the visit method is an array of AST nodes. So the AST, this abstract syntax tree, is this tree of nodes, and there are nodes for just about anything you might express in source code. There are class nodes, and there are method nodes, and there are parameter nodes. They're just anything you can express in source code, there are corresponding nodes. So the first element in this array is going to be the annotation node. It'll be the node associated with the magic number annotation, and I don't really care about that. What I care about is the second element in this array is going to be the class that was annotated. So in our case, it's going to be the foo class, right? Right here, I annotated the foo class with that magic number. So this is going to be the foo class. And what I want to do is I want to add a method to that class. And I'm going to go through a couple of iterations here. We're going to start with kind of the most flexible and most tedious, and then we'll sort of back up to a little bit higher level and make this less tedious as we go. But so what I want to do is I want to add a method to that class node. So we'll say method node equals new method node. And the first argument to the method node constructor, method node constructor is the name of the method that I want to create. The second argument, I'm not going to remember all these, the modifiers, and then the return type. So the modifier, I want it to be a public method, like that. I want the return type to be integer. There's a utility class for creating class nodes. I want the return type to be integer. Next are the parameters. The method is not going to accept any parameters. It's not going to throw any exceptions. And the last argument will be code. That's what I want. All right. Let's see. We want code to be a new return statement. And I want it to return a constant expression. That is the number 42. All right, let's take a look at that. So I'm creating a new method node. The method's name is getMagicNumber. The method will be public. I'm going through the arguments in order here. The method will be public. Its return type will be integer. The method accepts no parameters and does not throw any exceptions. This is an array of the exceptions that it throws. And then code is going to be the body of the method. And the body could be as complicated as we like. In our case, I want the body of the method simply to be a return statement that returns the constant 42. So I don't want to go any further down the path of the details of the Node API than that. There's a whole bunch of tedium down there. What I want to do is the minimum amount of stuff just to make this operational, and then we'll clean it up a little bit as we go. So I've created a method node. I've got a reference to the class that I want to add that method to, right? So now I want to call class node dot add method node. And that's it. All right. So when the compiler compiles, there's another piece we've got to fill in, not in this source file, but someplace else. We'll get to in just a minute. But we're going to get to a point such that when the compiler is compiling any class that's annotated with magic number, this AST transformation will be engaged. What's being passed into the visit method, the thing that we're interested in that's being passed in, is the second element in this array is going to be the class node that's associated with the class that was annotated. So in our case, the foo class. I'm creating a method called getMagicNumber. The body of the method is this. It's simply returning the number 42. And I'm adding this newly created method to the foo class, right? So once we get all the other pieces of the puzzle in place here, when the foo class is compiled, there will be a getMagicNumber method in that class. We need to go over here to the magic number annotation, and I need to annotate this like that. We want, what's the package name there? It's devoxx.demo.magicNumber transformation. That's the key right there that tells the Groovy compiler that anytime a class is annotated with this annotation, I want this transformation to be applied to it. All right. Let's see what we've got so far. Let's run this test. And we got a green bar there. So let's change the transformation to return a different number again, just to be sure our test isn't passing for the wrong reasons. There we go. And I'll run that again. So we've got a green bar now. So as the author of this class, all that I need to know is that the way to get all this magic number behavior, and in this case it's just one trivial method, but whatever behavior is supposed to be associated with magic numbers, all I need to know is what that behavior is. So in this case it's a method called getMagicNumber, and I need to know the way to have that behavior applied to this class is to annotate the class with that magic number. And then all this tedium is somebody else's problem. It's whoever is providing the library, the magic number library, has to write this complexity. And now I get to simply just annotate a class with magic number, and behaviors added to my class at compile time. So unlike some of the stuff we talked about earlier, where we couldn't call the do something method from Java, we can call the getMagicNumber method from Java, because the getMagicNumber method really is in the bytecode. This is all being added to the foo class at compile time. This code is being executed at compile time, not at runtime. So when the foo class is compiled, this gets executed, and what this is doing is adding a method called getMagicNumber to the foo class. Does that make sense? Questions about any of that so far? Yes, go ahead. Absolutely. So the question or the comment is that this looks really cool, but can I describe a real world example of where you might want to do something like this? So this happens all over the place inside of Grails. So in Grails, those of you who've done Grails development know that all of your domain classes have methods like save and count, and there's a bunch of common methods that all of your domain classes have. And there are a bunch of methods that are added to all of your controllers, methods like redirect and render and get params and get session. In recent versions of Grails, all of those methods are being added at compile time by AST transformations that are provided by the framework. So you never see them, you don't have to interact with them, you just know that as the author of a controller, you can call redirect and you know what to expect it to do. The way that the mechanism that was used to get that redirect method added to your controller is an AST transformation that's provided by the framework. In early versions of Grails, all of that stuff had to be done with runtime metaprogramming. We had to do things like controller.metaclass.getSession equals closure and controller.metaclass.getParams equals closure. Later on, as the framework evolved and the Groovy language progressed and introduced the AST transformation mechanism, we were able to refactor a whole bunch of stuff in Grails that used to be done using runtime metaprogramming and replace it with compile time metaprogramming. There are also a number of transformations that are provided kind of right out of the box by Groovy. So Delegate is a good example. It's let me create a class that uses that delegate. For some reason, my mouse cursor has disappeared. That's going to be problematic. There it is. All right. Let's see. So I want to create a Groovy class called something, right? So if I have a map called props and I say at delegate, so there's an AST transformation. So at delegate is core Groovy annotation. It's a Groovy provided by Groovy. And there's an AST transformation associated with that annotation. There's an AST transformation that's associated with this annotation. And what it will do is, so the at delegate annotation can be applied to properties in your classes. And what this transformation is going to do is it's going to recognize that this property is of type map. And what it's going to do is it's going to add all the methods that are in the map interface to this class. And they behave like this. Right? So the compiler, let's see, that's not what that does. That does that. The compiler is going to generate this method for you. That's one of the methods that is declared in the map interface. All of the methods that are in the map interface will be added to this class at compile time. So you would never type lines 8 through 10. Those get added by the compiler. So it may be the case, and further, what will happen is this class will be made to implement map. So you don't declare that this class implements map, but it will implement map. And you don't declare these methods. They're all added for you. So what that provides is a really simple mechanism for you to write a class that delegates to something else. And the way you're delegating to something else is all of these methods that are in the map interface, and there are a bunch of them, they're all added to this class at compile time, and they all delegate to the corresponding method in this object. So maybe you want to override just one of them. You might want to override the get method and do your own thing here. Instead of delegating to the props, you want to do your own get for whatever reason. It's an AST transformation that's making all that possible, and it's just drop dead simple for you to write a class that delegates to something else, and your class becomes, it appears as if it is that something else. So in this case, the something class is a map. The compiler will make something implement the map interface. All the map methods will be here, so I can create a something and interact with it just like it's a map. Right? Does that make sense? There are lots of ways to take advantage of AST transformations. That's just one of them. All right, let's get back to this transformation and take a slightly different approach here. Instead of all that, let's do this. Let's say In fact, what I'm going to do is rather than type all this, I'll cheat. And do that. Where did it go? Let me get that class back here. That's what I wanted. The idea there was to save myself some typing here. So instead of that code that we just had a moment ago, this is what we've got. So Groovy provides this thing called AST Builder, and it's a way to build up AST nodes in a little bit more readable. It's a DSL for describing those things as opposed to what we had just a moment ago. Let's do this. I want to get the other thing back here. My undo buffer is not there. But so what's happening is we're creating an instance of the AST builder and invoking this method called build from spec. And I'll just step through this and kind of describe what's happening. We don't need to get super deep into this, but I'll just step through this and describe what's happening. So we want to build a method whose name is getMagicNumber. The method is public and it returns an integer. These are the parameters. So if it accepted a parameter, there's a syntax for describing a parameter here. In this case, the thing does not accept any parameters. It doesn't throw any exceptions, and the body of the method will be a block of code, and that block of code simply includes a return statement, and the value of what's being returned is the constant 42. And so what's returned from this call to build from spec is an array of nodes, and I want the first one. It's going to be the only one, I think, in this case. The first one of those nodes is going to be this getMagicNumber method. So what I've got is a little bit cleaner, a little bit easier to look at mechanism for describing that method node that I want to create and add to the foo class. So let's get back over here and run this test and verify that we've still got green bars. There we go, and that worked. So the AST builder, what I was doing before is creating a method node and creating parameter nodes and creating class nodes that represent things like return values. And the AST builder is kind of a DSL that abstracts some of those details from you and just makes it a little bit easier to describe the nodes that you want to create. But even that is somewhat tedious. Let's take a look at another option. All right, any comments or questions about the AST builder before I move on? Let's take a look at one other approach. So here is a trait. So recent versions of Groovy support traits, and traits are they're related to compile time metaprogramming. Traits are a way to deal with to solve a number of different kinds of problems. So a trait it's like an interface, but the methods have bodies to them. So it's like a hybrid between a class and an interface. The methods have implementations to them. But how a trait differs from a class, so if this was just a class message sender, and I wanted to write a class that inherited this behavior, I could write a class that extends message sender, and now my class is a message sender and it has the send method. But because of Groovy's single inheritance model, since I extended message sender, I can't extend something else, right? I can only extend one class, and that's not true with traits. When I define a trait, I can write a class that implements as many traits as I like, right? I can write a class that implements the message sender trait and the foo trait and the bar trait. I can implement as many traits as I like. And what happens is effectively all the methods and all of those traits are mixed into the class that implements those traits. So it's a way to deal with the single inheritance limitation that both Groovy and Java have. So here I've got a trait that has some behavior in it, right? It's got a send method. The send method accepts two parameters. The first is a string and the second is a writer. And what the send method does is prints the string to the writer with a prefix there, the literal message. let's look at our message source spec, message sender spec. Here we go. So the sum class that's declared at the bottom here on line 26 is annotated with @message_source. And because I've annotated it with @message_source, @message_source is annotated with this, that causes this AST transformation, the messenger, there's a typo there, maybe I made the same typo in the class name, but this is the name of the transformation class that will be applied to all classes that are annotated with @message_source. So let's look at that class. I did in fact make the same typo in both places. That's why it works. So this is the transformation that's going to be applied to all classes that are annotated with that messenger annotation. So what the visit method is doing in this case is getting the class node that was annotated, and this is really the interesting part, is it's adding the trait node to the class. So let me circle back around and be clear what's going on here. So I've got a class called SumClass that's annotated with message_source. So SumClass is the class that's going to be transformed. And this is the class node that's associated with the message sender trait, the trait that has the behavior in it. And the way for an AST transformation to add a trait to a class at compile time is what you see here. So what this transformation is doing is making sure that the class doesn't already implement the trait, right? That's what this is doing. And if it doesn't already implement the trait, add the trait to the class. So by the time once the class has finished compiling, this class will implement the message source, message sender trait. It's as if you did that, but you don't have to do that, right? You just declare that you annotate the class with that message source. Annotating it with that message source causes this transformation to be applied to the class. And when this transformation is applied to the class, what it's doing is making the class implement the message sender trait. All right? And that test we were just looking at, let's see if that is in a green bar state. And it is. Both of those tests are passing. So let's take a look at the tests. The first test is asserting that some class does in fact implement message sender, and it does, right? If I take that off and run the test, that's going to fail, right? Well, both the tests fail because the some class does not in fact implement message sender. When I put the annotation back, the test should start passing again, and they do. Right, so the first test is just making sure that some class implements the message sender interface. The second test is calling the send method and asserting that it does what it's supposed to do. Right, when you call the send method and pass a string and a writer as an argument, what's supposed to happen is this string should be written to this writer with the prefix message colon. Right, and that's what's happening there. Does that make sense? Questions or comments about any of the trait stuff? So remember that a class can implement any number of traits. You're not limited to implementing one trait like you're limited to extending one class. So if we were to look at a Grails application, so I've just created I'm missing an X in Devoxx there, but that'll work. I'm going to create a controller called demo controller. And I'm going to compile this project. And the first time you build the project, all the dependencies have to be put in place. There we go. So now if I look in build classes main, that's what I want, Java P demo.demo controller. So I'm just inspecting the demo controller class to see what it looks like. Never mind all that stuff. right here, public class demo controller implements controller, implements async controller, implements tag library invoker, implements response. There's a whole bunch of traits that this class implements. So inside of a controller, there's a bunch of stuff you can do, right? You can call redirect, you can call respond, you can refer to params and session. All of those almost all of those interactions in recent versions of Grails are all rigged up at compile time by an AST transformation that's provided by the framework. And here you see some evidence of that. All those traits that you see listed there were all added at compile time. None of them are represented in your source code. Your source code just says class demo controller. And at compile time, the framework can recognize that your controllers are controllers, right? Because they're declared under the controllers directory and their class name ends in controller. So there's a mechanism inside the framework that will cause certain AST transformations to be applied to certain artifact types. Different AST transformations get applied to different artifact types. And some of those transformations are adding traits like you see listed here to your artifacts. So there's a different set of traits that get added to controllers versus traits that get added to tag libraries versus services. All the different Grails artifacts have different kinds of AST transformations applied to them and have different kinds of traits applied to them. Some AST transformations don't apply traits. They do fundamentally different things. But what's important there is that there's all kinds of behavior being added to your artifacts at compile time by the framework, and AST transformations are what enable that. So this happens all over the place in the Grails framework. Controller methods are all rigged up at compile time to do interesting things. So as an example, let me get this demo controller, right? So if you have a controller action that looks like this, right? By the time that controller action gets executed, let's see, the value that'll be passed as an argument here is the value of a request parameter called name, right? So this is the code that you write, and in here is where your controller action code goes. And what the compiler is generating is this. Right? So the compiler generates this for you, which allows you to not have to refer to params directly, right? You just declare method parameters whose name corresponds with the names of request parameters that you want access to, and something like this happens. If you have a domain class, a command object class, even more interesting things happen, right? So we've got a command object class called widget, and we'll have this thing be widget W. So what happens here is the framework, again, this is all, you write the code starting at line 10, and there's an AST transformation that creates all of this. Say widget, it'll call bind, it's actually a request. Data binding will happen, and then there's no good pseudocode for this, but subject W to dependency injection, then W.validate, and then some action W. Right? So all of that, and that's pseudocode. There's quite a bit more going on than just what you see there. But all that stuff that's between lines 5 and 11 is all being generated by the compiler. There's an AST transformation that recognizes that you've got a controller action that accepts a command object parameter. So all this stuff needs to happen before your code gets executed. So this is the method that the framework's actually executing. The framework never really calls your method. It calls this method at request processing time, and what this is doing is getting the widget object all ready to go, and then calling the method that you wrote. So AST transformations greatly simplify what would otherwise be a bunch of tedious code that you would have to write in controller actions to deal with something like that. There's one more example I want to look at. So Grails developers are familiar with this allowed methods thing. So what allowed methods is about is it's a declarative way to express rules for which HTTP verbs are valid for particular controller actions. So if I do something like that. So what's expressed on line 5 is that the sum action method is only valid to access the sum action method with a post request, and it's only valid to access the index action with a get request. So what the compiler generates for that is something like this. It'll say def sum action if not, let's see, yeah, so if not request method is a post, then send error, is it a 405 or a 403? I think it's a 405. Otherwise, invoke, and I'll leave the command object stuff out for now, right? So all this checking is added, again, at compile time because of the declarative rules that you expressed up here. So there are just lots and lots of examples of that all over the Grails framework, where behavior that's added to your artifacts is added at compile time, and AST transformations are what are making that possible. So command object initialization, like I just described, is all rigged up at compile time. Controller exception handling. So in your controllers, you can have a method that accepts an exception type. So you can say handle it SQL exception, right? And now, if any controller action in this controller throws a SQL exception, this method will be called, and the SQL exception will be passed as an argument. And the way that works is, again, there's an AST transformation that puts all of your code inside of a try-catch block that's catching SQL exception. And what this does is invokes your handle it method like that. So you don't have to put try-catch blocks all over your controller code. You can simply declare a method that accepts an exception type as an argument, and all of this, the try and the catch handling, is added by an AST transformation. Right? So again, there's just lots of examples of that sort of thing all over the framework. Properties that you don't want to be bindable, you can configure in your constraints block. You can say first name bindable false, and there's an AST transformation that rigs up all the data binding stuff so that when you do mass property binding, that property will be in the blacklist by default. There's all kinds of GORM stuff that's added using AST transformations. So all of your domain classes have a method called save, and a static method called count, and a static method called list. All those standard methods, not the dynamic finder methods, but all the standard named methods that are added to your domain classes by GORM, those are all added using AST transformations. There are a bunch of transformations provided by Groovy, so I just wrote a couple of transformations, one that dealt with our magic number thing and another that dealt with the messaging thing. There are a bunch of transformations provided by Groovy. Delegate I talked about, which makes it really, really easy to write a class that delegates to some other object without having to write all the delegating methods yourself. You can annotate a class with @immutable, and that tells the Groovy compiler not to generate setters for your properties, and it also makes all the fields behind your properties final, so it makes an immutable class. In Java, the default access specifier for fields and methods is package scopes, right? So if you leave the identifier off, then that property is package scope. In Groovy, the default access specifier for methods and classes and fields and properties is public. So if you leave the access specifier off, that method is public, which complicates marking something as package scope because the package keyword is already used someplace else, right? That's for declaring the namespace for your classes at the top of the file. So Groovy couldn't use the package keyword as the way to express that you want a particular method to be package level. So Groovy has an AST transformation, so you can annotate a thing with that package scope, and that tells the compiler to mark that property or that method as package level. It turns out that package level is not used very often, so that's it's reasonable that that's the most tedious thing to do, right? The thing you most often do is write public methods and public classes and public properties. What public properties means is a private field and a public getter and a public setter. So that's what Groovy does by default. And if you want to do the unusual thing, like make a package scope method, then there's a way to express that. You simply annotate the method with that package scope. If you annotate a class with that singleton, then there's a bunch of stuff that there's an AST transformation that does a bunch of stuff to your class. So the class will be made final. The constructor will be made private, so no one can create an instance of that class. There'll be a public field added to the class called instance, and that's the way you get a reference to the singleton instance. All the static one-time initialization of the singleton or of the instance property is all rigged up for you at compile time. So writing singletons is much more clean in Groovy than it is in Java. You write the class just like you normally would. You don't have to deal with the constructor or the final class business. Just write a class as if it weren't going to be a singleton, and then annotate it with that singleton, and all the stuff I just described will happen. You'll get, the class will be final, there'll be a private constructor, and it'll be singleton friendly. Yeah. So those are all AST transformations provided by Groovy right out of the box. There are a bunch of others. So those combined with the examples that I stepped through hopefully provide some kind of picture for some of the capabilities of the AST transformation engine supported by Groovy. Questions or comments about any of that stuff?
You have a question about these traits?
Yeah.
I never used them. I didn't know Groovy had it like added them recently. Can you reference the super on a trait?
The question is, can you reference super in a trait? You can reference, the more common question is, can you reference this in the trait? And the answer to that is yes. So in here, if I refer to this, that's not going to be message sender. It's going to be the thing that implements the message sender interface. I don't know what super would even mean here.
That's what I meant.
This is what you meant?
Yeah.
Yep. So inside of a trait, you can refer to this, and the compiler will find all of these references to this and make them point to the thing that implements the trait. So you're not pointing to message sender, you're pointing to whatever class is implementing the message sender. It turns out that that's important, right? You need to be able to do that, and so that does in fact work. I don't know what super would mean in a trait though, but this behaves the way that I just described. Any other questions or comments? Anything else you'd like to see?
Yeah, what if you have another trait with the send method?
Yeah, so if you have multiple traits with the same methods, there's a disambiguator thing. So if I said trait foo, let's do this. Where are we here? That's not it, that's it. The same problem can come up when you implement, when you use the delegate thing. Let me come back to that in just a moment. So if you delegate to two different things that each, so if you had another thing that also had a put method, delegate to something else like that, and the map interface and the something else interface each declare overlapping methods, the compiler will complain about that and tell you you can't do that. And I'm not sure what happens with a trait when you do the same thing, but it looks like that's compiling. But what I don't know is what we're actually generating there. So I don't know the answer to that, but that's a good question. So I'll track that down, and if you like, send me a note, give me your email address, and I'll get back to you on that.
I think the last one wins. The last one.
You think it's order dependent? I don't remember if that's the case or not. Are you guessing, or you think that's how it's implemented?
I read
Okay, so at least someone wrote at some point that the last one in wins, and that may be the case. Any other questions or comments? Good. I'm going to write a test and verify that the last thing in wins. If you're interested in spectating that, that's fine. But that's all the material that I've got and wanted to go over. Again, my email address is brownj@ociweb.com, and on Twitter, Jeff Scott Brown. If you have any questions or comments at all about Groovy or Grails or anything we can do to help you out, please let me know. And thank you all very much for your time.